is happening? Okay, we'll start. It's 6:05 already. Could you please confirm that you can hear me and you can see my screen?
Yes, sir. It is visible.
Okay. Please mute yourself. Okay. Good evening. I am Shaptush Chide. I'm a PhD scholar at IIT Bombay, Electrical Engineering Department. I am working on machine design for my PhD, and I take this weekly interactive session for the course of Power Electronics, Fundamentals of Power Electronics, which is instructed by Professor Illumanan from IIS Bangalore. This is the seventh week of this session. Since we are running 1 week late, so we shifted our topic so as to get synchronized with the main course. So that was some 4 weeks back. So today our topic of discussion is isolated um, DC-DC converters. Now, when we say isolated, that means the DC-DC converter can have sorry, the DC-DC converter can have multiple blocks, at least two, which are connected through galvanic isolation. Means they are electrically isolated. So say a 4-port isolated converter may look like this. All these four windings are connected to the same core. This transformer contains four windings. Now, as you can understand that transformer is of much importance in the study of isolated DC-DC converters. Now, the transformer that you study in your electric machine course and the transformer that you get here in the isolated DC-DC converter, when you are analyzing or writing equations and all, there is no difference. They are exactly the same. Okay, so you need not think that this is some other transformer. This is exactly same transformer what you have in your electric machine, but the transformers that we have in our power system, that is a distribution transformer, power transformer, or other isolation transformer, all those transformers in power system and the transformers in power electronics are different in terms of frequency. The transformers of power electronics are of high frequency transformer. Why are they high frequency transformers? Primarily because the converters themselves operate at high frequency, and secondary reason, and this which is also very important, is that just like an inductor of a DC-DC converter, the size of a transformer also, not lower, also reduces with the increasing frequency of the transformer, increasing operating frequency of the transformer. So many a times you will get to see that say in PV systems where they connect the system to the grid, or in other applications also. So if you have the PV cell here, and if you have say a DC-DC converter here after this, what they do is, if there is a requirement for step up or isolation, Here itself they give one transformer. Then maybe here they give an inverter and feed it to the AC system, right? This transformer could have been given here also, but say if this transformer was working at 40 kilohertz, here we would have required a 50 hertz transformer of the same power rating, but this would be higher, larger. This transformer would be larger. Why so? You can simply say it from the transformer flux equation. The flux equation, oh, sorry, the voltage equation. That psi is, we know, n d phi. Sorry, psi is n phi, and phi is, say, in a transformer it's sinusoidal, say phi 0 sin omega t. Now if you do the EMF E, which is d psi dt, that comes out to be n omega phi naught cos omega t, right? So you see, for the same EMF, if you have a larger frequency, you can operate the transformer at a lower flux so as to have the same EMF, right? That means, so higher frequency means smaller flux. So that means we can have a smaller core also. Core. We discussed this last day that we have restriction on the value of B. The value of B. We cannot operate beyond certain point. It will start drawing a lot of magnetizing current. This is one thing. Another difference, although that does not change anything theoretically but changes many things practically, between the power system transformer and the power electronic transformer, the high frequency transformer, is the core material. The core material in power system or low frequency transformer, that is electric steel. The same materials with which electric machines are made, only thing is that for transformer it is grain oriented steel. For high frequency transformer it cannot be electrical steel because that would give rise to a lot of eddy current. Okay, it increases frequency, eddy current, and increases losses. So for high frequency transformer, the primary element is ferrite. There are other high frequency transformers which go for very high frequency, quite large, and they use, I think, some nano particle based, but they are very advanced thing. uh, Primarily for our application, say even till 100 kilohertz also we can use this ferrite core transformer. Now the name of the material is not the only difference. The difference, one of the very important differences, is that for electrical steel you can design the operating frequency, or in other words the knee of the BH curve lies at around, say, our good machines, good materials, 1.3, 1.4 Tesla. Whereas for this is for electrical steels, whereas for ferrites it's only 0.2, 0.3 Tesla, so much lower than them. But still we have to use ferrite. Why so? Because ferrite cores are like this. They have small particles of ferrite which are insulated separately and they are pressed together by some machinery, so eddy current cannot flow between them. So we are relieved of high frequency, high, I mean, core losses. Core loss is a direct function of frequency, f squared, around f squared, or f to the power 1.6, depending on which loss we are talking about. So this is the main difference, practical difference, between the transformers of our power electronics and power system. But when you are writing equations and all, it doesn't matter. Okay, we will need not even think about it. Whatever transformers we had there in power, we study in our electric machine, the same thing, everything, the same thing happens. Everything holds good. One important thing that we come across a lot in isolated DC-DC converters is the dot convention of transformer. This is nothing but the polarity or the respective polarity of the transformer windings. I think I discussed this once. We'll still look at it once again. So, what does this dot mean? So, if I have a current entering the dot of one winding, and if this current is increasing, that means on the other winding, the dot side will have a positive polarity or higher polarity than the undotted side. Okay, so this thing can be well reduced to this. Hmm, I have this. Now I will not draw the coupling anymore. I am trying to decouple. So instead what I will have is a voltage source, dependent voltage source, and it will be M di1 dt. Which is I1? I1 is this. Similarly, something will also come here because a current is also flowing, I2. And this is the same M di2 dt. Now notice the polarity I have shown for this dependent voltage sources. This is because I have given the dots like this. If this dot was here, then these things would have been reverted. Okay, but the thing is, while studying these converters, we will not go into this much complex equivalent circuits. We will simply think it this way. See, what I said is, if this current, current that is entering in this terminal, if this is increasing, then there is a positive here. Now we know that, see, this is a transformer, okay, so an inductor you can say. So we know that voltage across inductor is L di dt. So increasing current means in positive di dt. That means the transformer must be having a voltage like this in here, in this terminal. So you see, if I have a dot, if I have a plus on the dotted terminal of one winding, we will have plus on the dotted on the other winding also. If we have plus on the undotted, we have plus on the undotted on the all other, not only for this primary secondary, for if you have a tertiary also the same thing. Okay, so we will just look into it in that way. That's easier for circuit analysis. um, so transformer is an important thing for DC-DC converters, isolated DC-DC converters. And in last class we mentioned that, say, our last topic of discussion was this, one second, yeah, was this voltage gain. Okay, voltage output by voltage input versus duty ratio of a boost converter. That the theory is d by 1 minus d. It says that ideally if we keep approaching d equals 1, we should be getting infinite voltage, but that never happens because of non-idealities. Sorry, practically it is something like this. It drops to 0. But what if we need a large amount of, and this thing is true for buck also, you cannot keep on reducing d at a very low voltage value of d. uh, you will not get that much of drop, that much of stepping down, and the losses will increase a lot. But what if you really need such large step up, means such large boost or buck in the voltage level? That is achieved by the transformer. There is another reason why DC-DC isolated converters are popular. All right, so that is some introductory discussion. Now I will take doubts from you.
Sir,
Yes, go ahead.
basically for from your explanation for the same EMF
Hmm.
to reduce the flux in the core,
Hmm.
uh, we are going for a high frequency.
Hmm.
Uh, so the material which supports that high frequency and give less loss is the ferrite.
Yes.
That's why we are using this material.
Hmm.
Uh, Sir, the flux density the maximum flux density the ferrite can allow is you have said it is zero point 0.2 to zero point 0.3 Tesla.
Yes, I understood your. So you see, the difference here is six times, more or less six times, right?
Okay, sir.
More or
Yes,
less
sir.
six times. But the increment of frequency is more than six times. Say for our power transformer, we have 50 hertz. The
Uh,
power electronic converters, they start at 10 kilohertz maybe.
mm.
So
So it almost
that is, I mean, when you say 10 kilohertz to a power electronics engineer, that is quite low frequency, quite low frequency.
mm.
So the minimum increment is 200 times,
Okay.
while the reduction in the torque, in the flux density, maximum possible flux density is six times. Our increment of frequency is 200 times. That is minimum. Maybe you will be making circuits of at least 100 kilohertz, like that. So overall the size reduces.
Mm. Okay, but sir, the the current we need to make to flow through the magnetizing winding should produce the flux which is less than this zero point 0.3 Tesla. Uh,
Yes.
okay, sir. Sir, coming to this dot convention,
Hmm.
we have drawn this magnetizing. Sorry, this mutual flux, this mutual component,
Hmm. Hmm.
MdI1 by dt.
Hmm.
Sir, in this, no, this MdI1 by dt, this polarity, suppose we take one cycle of AC voltage at the input, at the input side, sir, this instantaneous polarity of the mutual voltage will be varying at each moment, right? At some moment it will be at this polarity, at the next moment it will be a different polarity.
Yes, that is why I have written lowercase I here.
Mm.
See,
Okay,
there's a lowercase I, and
okay,
when I am saying it is mdi by dt, mdi
ah,
dt,
okay,
this I is instantaneous, and this I is nothing but this I, right? This
ah,
GIDT
yes, sir,
DIDT.
yes,
That
sir,
means suppose at some instant you have this I1 flowing in this direction,
going out of the dot,
and it is say reducing. That means your DIDT is again positive.
mm.
Suppose it is in this
Yes,
direction, but increasing, it is negative. So this
negative,
whole thing is taken care of when I am writing this DIDT. Both the direction and its change,
ah,
both are taken care of.
okay. Sir, at that time,
Hmm.
what is the polarity of voltage on the inductor, that is self-induced self-inductance?
Which time?
Suppose if M is in this polarity, so on the secondary side, M dA by dt is the mutual voltage.
Hmm.
There is an inductor connected on the top of it.
Okay, see, the thing is, we have, say, I have V2 here, right?
Mm,
Now, this has some inductance.
mm,
So we have some voltage. So what we can write is V2
ah,
equals, uh, if you consider R also, then I2
mm,
R2
mm.
plus
Okay.
L2 di2 dt plus
Ah,
M di1 dt.
okay.
So this voltage
So,
depends on not only on the current of this, but also on the current of the secondary side. Now if you consider open circuit, then V2 depends only on the current of the primary.
mm.
If you consider open circuit in the secondary, at that time
Okay.
it only depends on the mutual voltage that is coming.
Okay. Sir, with this setup, can we approximately say what will be the phase difference of this current I1 and I2?
That depends on the load also, right?
Hmm. Okay.
Because you are getting some voltage here.
Okay, sir.
Suppose this is an ideal transformer,
Uh,
so there is no magnetizing inductance,
yeah.
so and no resistance also. So even if there is a load, the voltage V2 is M di dt, right?
Mm.
Then the voltage V2 is M di1 dt. Now if you have a pure resistive load here,
Yeah, on the
then
secondary.
the difference is 90 degree.
So I2 lakhs I1 by 90
Hmm.
degree.
And then if you have other loads, then that depends on the load power factor.
Okay.
That is what happens in a transformer, no ideal transformer. If you have the flux here 5, voltage here V1,
Okay.
then this is V2, then primary current is along this 5 because that is what is creating the flux. Secondary current for a pure resistive load is in phase with V2. Then we take it refer to the primary, add them.
That is a total component.
No,
I
I'm
know.
doing something wrong.
That's I mu working I mu and IW will be there.
No, I1 is the primary, sorry. We are considering ideal. There is no core loss component of the current.
Okay.
Okay, anything else? You have no question from flyback forward or maybe transformer also.
Sir, in forward converter,
Hmm.
uh, sir, can you please explain that lossless core reset? Uh,
Lossless core reset. Have you understood why at all a core reset is required?
yes, to a certain degree, yes.
Huh? Two?
To a certain extent, yes, sir. That is with this how at when the switch is on, the flux is building up in the primary
See, the
winding.
thing is, uh, if we had an ideal transformer, what do we mean by an ideal transformer? An ideal transformer is like this. That it does not have any magnetizing inductance. That means it does not require the core of the transformer. The core of the transformer does not require any net flux for the transfer of power. So if you have one winding say here, another winding say here, if you have a load, then as soon as you give some current, the exact current gets reflected
Mm.
like this, and it draws no magnetizing current. It is infinite Lm. But a real transformer, practical transformer, that has some Lm. Okay, and this Lm actually accounts for the stored magnetic field the stored magnetic energy in the core. Okay. Now for a forward converter, here itself, if I draw a forward converter, remember I am not adding any more uh, winding here. This is
Yeah, magnetizing winding, understood, sir.
just the equivalent circuit of the transformer. Something is wrong, color is not changing. Oh, yeah. So if I have the forward converter here like this, see, a forward converter is nothing but a isolated buck converter. Have you understood that, or could you
Yes, sir.
realize that forward converter is nothing but an isolated buck converter?
Buck converter.
So this is the inductor, secondary inductor. Now what is happening is, say this is my switching period. I am turning it on somewhere here, the switch on for this period, and the switch is off for this period. Okay. Now when the switch is on, see, there are two components of current here. One is the I1, right, which is flowing through the primary winding of the ideal transformer. This part is the ideal transformer. This whole thing is the practical transformer. So I1 is flowing through the primary of the ideal transformer, and I2 is flowing to the primary winding of the ideal transformer. So basically between I1 and I2 we have this relation I1 by I2 equals N2 by N1. But there is another current Im that is flowing. So the source current Is is actually the summation of I1 plus Im. Okay. Now if you do not, it doesn't matter whether the transformer is ideal or not, but the I1, it will look like this. Just a minute. I1 will look like this. And similarly will I2. They are linearly related. It will look like this. But the thing is, when this switch was closed, this current built up in this magnetizing inductance. If I open this switch now without any other path for this energy to go away, as we discussed in some other classes also last day also, there's this stored energy of inductance must go somewhere, and since the current is suddenly interrupted, a voltage L di dt, in this case Lm di m dt, is developed by the inductor, which is very large and that comes across the switch, and that will destroy the switch. Basically the stored energy will suddenly get waveform across the switch. I will show, suddenly get dissipated across the switch, so that will get destroyed. So we have to give this thing a path to flow. How to give it a path to flow? The best way is to give it through another winding or the tertiary winding of the transformer. Remember, this is connected on the same, this is wound on the same core. Okay, so these three windings are on the same core, right? And what we want, okay, let me remove the diode for now. What we want this power to go back to the source. The source is like this, so we want this power to go back to source, and when the switch is closed, then this winding should not operate, so we must have a diode like this. we must have a diode like this. The next question is, okay, we know we need another winding, we need another diode, but when I am making the transformer, how should I wind the third winding? Or in other words, in this circuit, where should I put the dot? Should I put the dot here, or should I put the dot here? That is the next question. How to understand that? Now, if you look here, let me draw it in a bigger way so that you can see. It was the primary winding. Okay, I'm drawing the primary winding also. So this is the primary winding, and Im was flowing here, and it was increasing. It was increasing when the switch was closed. Now what is happening is, when the switch is open or turned off during this time. So if I draw Im, it's difficult to draw vertical lines here. If I draw Im, I was increasing. Now it will reduce through this winding, right? Sorry, reduce. So this current will now flow through this, So what do we have now? The voltage here, if I write it as V1, the primary voltage, V1 is Lm dim dt, right? And it is reducing, so it is negative. The same voltage is coming here, the whole voltage. So basically in the negative terminal we have a minus on the, so on the on the undotted terminal we have minus, on the dotted terminal we have plus. If you look here, so now this kind of, did I do something wrong?
Sir, actually this is magnetizing winding and this is the primary winding.
Yes, magnetizing primary winding.
The inductor will need, the magnetizing winding needs another winding to dissipate.
Yes. No, see, it is here. It had some current. This magnetizing winding had some current going through it. So
Even
this
the
current will keep flowing. This current will keep flowing, right? And it will reduce. So we have V1 negative. V1 negative means the actual polarity. I am drawing the actual polarity of voltage, which is this, right? So the under terminal is plus. Now if you look on the secondary side, it comes like this. So this will reverse bias this diode D1. So secondary side, no current can flow. But for a transformer, for an ideal transformer, this I1 N1, okay, let me not write it here. Ideal transformer, this I1 N1 plus I2 N2 plus I3 N3, that must hold good. I2 N2 cannot be non-zero. It has to be zero because it has no path. So I3 must now flow, right? I3 must now flow. So what is happening? As soon as I'm opening the switch, this current now flows here in this loop, the primary loop, and it impresses a voltage in this fashion, right? And I want this power to get transferred to this tertiary winding and flow back to the supply. So what do I want now? I want this kind of polarity to appear in the tertiary winding. Then only the power, this diode will get forward biased and the power will be fed back to the source. Now here what did I have? I had a negative, just a second. For this kind of a real polarity, I want this kind of real polarity on the tertiary. So I had a negative on the dotted side. So here I will want the dot to appear here. Here I will want the dot to come. So I will wind the transformer in such a fashion so that the dot comes here, or you can say it's actually the other way around, that we make transformer cores maybe like this. Then we have three windings. We do polarity test. We mark the dots, then connect them in such a fashion that it looks like this, that the dot of the tertiary comes here at the cathode of the diode.
Sir,
1 minute, have you understood why it is coming at the cathode of the diode?
yes, sir. Because at
Okay.
that time the voltage across this winding will be greater than the source winding, so it will be
Yes.
forward biasing this diode.
Okay. One question came, is that I will take your question. Just one question came in the comment box. How to get the switch voltage IS? Okay. So basically we are now, sorry, not IS, switch voltage VS. So this is the switch voltage that we are trying to find. Now, when the switch is closed, that is during this interval 1, the switch is carrying current. So the switch voltage at that time is 0. Sorry. Switch voltage at that time is 0. And when the switch is open, then that time it is blocking some voltage. So it is like this. It is 0. So we have to find out this amplitude, right? Now, what we will do is we will draw, we will write KVL in this loop. Starting from here, we will go through the primary winding, switch and come back. If I do that, then say if this is my DC supply voltage V in, then my KVL equation becomes equals V in equals V1. V1 polarity is like this, V1 plus V switch, right? Now I have to find V1. Now you see what is happening when the switch is open. There is some galvanic interaction between the windings 1 and 3, right? Because the energy is being fed back to the source, so there is a galvanic interaction between 1 and 3. Okay. Now what is the voltage across this winding 3, across the tertiary winding? The voltage across the tertiary winding is V in, right? Because this diode is now forward biased, it is giving power to this. The voltage across tertiary winding is V in. But you see, V in with this polarity only. If I write plus here, if I write minus here, but since uh, we have dot conventions, let us follow the dot convention, that all our pluses we will put on this side. So if I write my V3 like this my V3 becomes minus V in, right? So if we put all the pluses on the dot side, then only we can write that V1 by V3 equals N1 by N3. You see one thing, the biggest difference between, yes, I will talk to you. The biggest difference between our power system transformers or machine transformer that we study and what you are studying now is all the voltages that we are writing now are in instantaneous value. Okay, so in power system or machine you have studied V1 by V2 is N1 by N2, where these are in capital means RMS, but this thing is valid in instantaneous voltage terms also, instantaneous current terms also. So if I put plus signs in all that at all the dot terminals, means our assumed positive at all the dot terminals, then only we can write with polarity V1 by V3 is N1 by N3, whereas my V3 is minus V in, right? So my V1 is N1 by N3, N1 by N3 times V3. V3 is minus V in, so minus V in plus Vs. So the switch voltage that we have here is 1 plus N1 by N3 times V in. Okay, I will take question from you, RS. You are going to say something, but someone raised a hand and said hi. What is your question? Krina Murthy. Yeah, you can unmute and say and ask your question. Okay, I'm going to lower your hand. Okay, anyway, RS, you were going to ask something before I started this switch discussion. Okay, I see Shanti has joined. She asked a question last day about this. Could you solve this, Shanti? This is actually a very easy question. I couldn't think about it in the last
Yes,
class.
sir, I could able to solve, but the question is like to the output current I naught,
Hmm.
this Q3 I will get added, sir.
Oh, okay. That was your doubt. But I think in the
Yes,
lecture
sir.
it was okay. Okay, I think in the lecture it was not considered. I was watching. They say that if this is the output current, this current you can always neglect. If this is the output current, I
Okay,
naught
okay, sir.
is I naught, then the voltage here is simply V naught plus V naught plus what?
I not into
I
RS.
naught
I
into
not
RS.
RS.
So basically they are neglecting this emitter current. So what I can guess why this is possible is that if we
Okay.
have mm,
हाँ
could you
हाँ
please
एक
mute
मिनट
yourself?
चालू करूँगा
Mr. Dhananjay, could you please mute
आते
yourself?
आते हैं
If we have VCE versus IC, just a minute. Uh, Something like this, and this transistor must be operating somewhere here. That's why this current is being neglected. I do not find any other explanation of it.
Reason. Okay, sir. Oh, in a discussion forum, I asked sir was like telling, I asked regarding IB current. IB is negligible. Beat of this
Hmm.
Q3 is taken high. Oh, but I was having doubt with IE. Will this IE will get added with I naught or it is a negligible value IE also?
It is neglected in the lecture, but I thought that maybe it's
If beta
must be
is
operating
high, then
somewhere
IC
here.
will be high, then IE will also be.
No, but again, these statements that beta is high, so but these things all we can make when we are sure that it's in the active region. Otherwise, I don't know whether we
Ah,
can say, isn't it? Saturation we cannot say.
yes, sir.
So maybe they have some
Mm.
design procedures in which they make sure
Yeah.
that at steady state this collector emitter current is small so that they can neglect it.
सर
Okay.
Yes.
sir here this in this Q3
Hmm.
the power rating of Q3 can be the collector current rating of Q3 can be very minimal, which is less than the very much less than I naught, so we can So,
Yes, that is true, but you have to make sure that that much current is not flowing through it.
what's
How
it?
that is done, I'm not sure.
That is the collector current of Q3 is equal to the more or less will be approximately equal to the base current of Q1.
These three currents. Oh, there was another current.
They are saying they are diverting that current IB1 through Q3.
Something like that. That if you have a large current, then this voltage increases. This voltage increases means you have more base current, so more current gets diverted here. So this thing then comes. This thing becomes means more resistive, and the current reduces. Something like that they said. But at steady state, this current is low. I think this is the only possible explanation, that they have somehow designed it to be somewhere here at steady state. Means there is when there is no disturbance, when the circuit is not going through any change at that time. Otherwise, this problem is easy, but with those assumptions only, that this current is this current only. All right, questions from here. Isolated DC-DC converters. So in forward converter, there is equation that relates N1, N2, and N3. There is no equation that relates N1, N2, and N3, but there is a relation that relates N1 and N3. Uh, the relation between N1 and N2, that depends on how much boost or buck you need at your output with respect to your input voltage, because for a forward converter your output voltage is input voltage times N2 by N1 times D, just like a buck converter with a transformer. Similarly, flyback converter is a buck boost converter with a transformer. So it's like this. So N2 depends on what output voltage you need, but there is a relation between N1 and N3 that you must follow so as to avoid staircase saturation. It's very easy to show. Say if you have, so this is the primary winding, secondary is not of much importance we are talking about, and this is the tertiary winding, like this. This one is not another winding of the transformer, this is the magnetizing winding of the transformer, whole transformer. Okay, I made a mistake. Like this, right? Now when the switch is closed, okay, during on state, you have V in here. This V in voltage is impressed across V1. So during on state we have V1 equals V in, which is also equal to Lm dim dt, right? Since it is an inductor and the current rises linearly, we can say it is delta Im by dTs. So the increment in current during on time is given by V in dTs by Lm. Now during off time, this thing is already discussed in the lecture, or I am just repeating it?
It is discussed, sir.
It is discussed. Okay, so since I have started, I will quickly complete it.
Okay.
During off time, what is happening? This inductance, I mean this diode is now carrying the current so that the power can be fed back. So we have V in being impressed like this. So we have V in being impressed like this. Yes, so minus on the dot terminal plus. So during this time what we have is we have V1 equals minus n what n1 by n3. It is being transferred from n3 to n1, so n1 by n3 V in. And since the current is still flowing like this, we can say this is equal to L delta I by 1 minus d ts. Now what we have is delta I is minus n1 by n3 V in 1 minus d ts by L. Now ideally what we will want is, or I am ideally what we will want is how much the increment in current was, that at least that much should be going away. Why did I say at least that much? You can design it in such a fashion that uh, much before the switch is turned on once again, the current is dissipated away. You can design it in such a fashion also, but since we're trying to find out the boundary condition, so this should be equal to this by magnitude. Now, if you equate this, so what we will get is n1 by n3 by magnitude I'm equating. So V in gone, T is gone, 1 minus d, everything is gone. Or I'm making some mistake, just made V in TSL, V in T equal d. So this is the relation. The relation is n3 by n1 taking this side, so 1 by d minus 1. So if you maintain this relation, what will happen is the current in inductance will increase, it will decrease, and from here again it will start increasing. Or in other words, if you have turns n3 and n1, whatever value of d you get from this equation, that is the maximum value of d. You cannot operate this forward converter at a value of d more than what you get from here for this given turns ratio. All of you have understood the working of flyback converter?
Sir, there are some doubts.
Yeah, go ahead.
So one thing is that the magnetics actually uh, magnetic design in flyback is very tricky. So how to sure shot design of magnetics of flyback can be done.
Okay.
That is a problem.
I do not have very well experience in flyback converter design. I designed and made some during my masters, but those were not very high-end flyback converters. Only for project purpose I made, but they used to work. Okay, they used to work. But I will try to give you some insight from what I have understood from there. So, okay, now we will shift our discussion to flyback. Before going into flyback, we will say some general things. These things actually help me to understand the operation of flyback converter. Say this is an inductor. Okay, now what we always say, we say that we cannot change the current through an inductor very first, and that statement we write mathematically in this fashion: V equals L divided. That is, if you try to change the current I which is flowing in this direction, inductor will oppose that by imposing a voltage in this polarity. There is a thing, but this is not the fundamental statement. Why is not the fundamental statement? We will encounter while studying flyback converter. So this is the flyback converter, this is inductor. You can think later that sometimes we study forward converter first, assuming that the transformer is ideal, then we see what will happen and what we have to do if the transformer is non-ideal. Flyback you can never study assuming it is a an ideal transformer.
Transformer.
In fact, it actually
It
works
is
like a
not
coupled
transformer.
inductor. Yes,
It is-
it acts as a coupled inductor. Flux must flow through the core. Flyback with ideal operation, you can assume the flux is not flowing through the core. It's only energy transfer from primary to secondary. But flyback for forward, but flyback, it's essentially storing the energy then giving it back or giving it forward. So it can never be operating with an ideal transformer. But anyway, this is a flyback converter, what it looks like. The thing is, when we are turning on, say this is the on time, we turned on the switch for this duration and kept the switch turned off for this duration with switching pulse. Now if this is my input current I in, it is like this. But the question is, if an inductor current can never be interrupted, how can I at all operate a flyback converter? As soon as I close this, as soon as I open this switch at this interval, this switch is gone. The whole inductor current, the whole inductor stored energy that comes across this switch and it destroys the switch. So what is a more general statement? The more general statement is an inductor does not allow the change of the flux linkage through it, and that is given by our Faraday's law. Sorry, V is d psi dt. Now we can analyze the operation of a flyback converter. How would we do? So when I in increased, the flux in the core, I am writing flux instead of flux linkage because flux is the common thing for both the windings. Okay, so the flux increased. Now as soon as I interrupted the current, this flux will now try to reduce, but it cannot reduce through this, means it cannot induce a current into the primary. So this will reduce while a current is being introduced or is flowing through the secondary. You can make this discussion even more interesting by actually drawing a transformer with senses of windings. During my initial days of studying flyback converter, I used to do like this. So if you draw in this fashion, then you have dots here, dots here. Now you draw the circuitry and all and try to analyze the whole thing by looking at how the flux flows. You will see that when you open this switch, this secondary winding must turn on. This must turn on. I mean, this must give a voltage like this, which will turn on the diode. You can do this study. So okay, what we are discussing, and since I in now like this, when the flux is reducing, I2 is like this. This is I in, this is I2. please. Now coming to the design of magnetics. So first thing that comes is we will design it from the ideal point of view. Now if you look here, you see, uh, what to say, look at the flux of this transformer core. Okay, so it has some non-zero value, right? Now I can design this transformer in this fashion also. I can design the transformer so that the flux is like this also. All the equations of flyback converter, of continuous conduction mode of flyback converter, they hold in all these three cases. Now for flyback converter, it is always customary to design the converter at the design the converter and the transformer at the DCM CCM boundary. DCM CCM boundary. You see, in this case, unlike a buck converter or boost converter, the DCM or CCM will be defined by the flux of the core. If the flux of the core is, say, something like this, it is DCM. There is no inductor here. DCM. So it is designed at the DCM CCM boundary. Why so? So that your peak flux reduces, your average flux reduces, and you can have the smallest possible inductor inductor size. That is one thing. Another thing, although we did not care much about it, means we did not have that much of, what is it, that leakage is important, because leakage of the, say, if you take the whole leakage on the primary side, because when you open the switch, the stored energy is going to the secondary, but the leakage energy is not going anywhere. It is anyway going to get dissipated across the switch. So we will anyway need a snubber, RC snubber, RCD snubber maybe. But smaller the leakage means smaller the lost energy in every cycle, and higher the efficiency.
But sir, one question is that if we are having a turns ratio very high, we cannot escape from this leakage inductance. For high
Yes.
voltage transformers, we have to
Hmm.
have turns ratio very high,
Hmm.
and there we cannot neglect this leakage inductance. How it is not possible. So in that case, what we have to do?
Actually, transformer design itself is a very vast topic. High frequency transformer design. I have colleagues here who are doing PhD on it, so I have almost zero idea on that. But I have seen them having, organizing the windings in different types of layers,
Yes,
using foil windings and all to reduce losses and leakage.
yes, yes, yes.
But those are very high-end topics of transformers. I don't have much idea.
But we have to design transformers as a part of our designing
Yes,
supply. We
yes,
cannot escape that.
yes, we cannot. But the way you are, I mean, mm, where we are going with this discussion, that is not
We
exactly
didn't.
my.
Okay, that is fine. But here the in magnetics, it
Mm,
is a coupled inductor. It is a inductor has to be that has to defined with the design with help
yes,
of leakage air gap between introduced in the path
yes,
length of that flux.
yes.
Okay, the air gap, how to define that slope of the BH curve, in what the degree
Okay,
it has to be there.
okay. I
Because
will tell you what we used to do.
huh,
Mm,
okay.
I have confidence in this method only because the whole circuit worked.
Hmm.
So I am not sure whether this thing is there in any textbook. So you see, this is the current I in. Okay.
Okay, okay.
So we have, say, I define this peak as I2.
Hmm.
Just take the pen drive. Okay, sir. We'll take. And I define this as I2, and this I define as I1. Okay. Now, if we look, the average value of the input current I in is given by I1 plus I2 by 2 times D,
Hmm.
right? Now, the average power that is given to us, say, maybe you will be asked to make a 10 watt, 15 watt, 25 watt flyback converter. So the average power is then V in times I1 plus I2 uh, by 2 into D, right? So this is equation 1. Another equation is V in equals Lm. If I write as delta I, since it is linear, so delta I in by dTs. Okay. So what is delta I? Delta I is nothing but I2 minus I1, which comes out to be V in dTs by Lm. Lm is the magnetizing inductance. Okay. Now, the next thing that comes is, just a second, and delta I is it.
Sir, you have taken I1 as the initial value. From here it is rising the current, isn't it?
Yes,
Yes. Delta I is equal to I2 minus I1.
I1. Okay, and that is it. So we have two relations, I1 plus I2, I1 minus I2.
Hmm.
Now the next thing that comes here, what is the ripple that you want to allow?
Hmm.
What is the ripple that you want to allow in the transformer uh, flux density phi? This
Fine.
thing you can this not flux density, sorry, the flux phi. This thing,
Actually, that delta ripple delta phi is the working zone of the flyback,
yes,
and that has to be limited with the B max minus some
yes.
ripple.
So
Okay.
somewhere here maybe we have to restrict it.
Restricted.
So like this. Now what we can do is phi is Li. Just a second, how it would come, I1, I2. Let me recall, just a minute. I1, I2 means if I divide
That
this.
be H will be Ni by Lm.
No, no,
This.
I'm no, let us not go to the magnetic circuit right away. We have some way to do.
Okay.
Um, Let me do it in this fashion. Say delta I, if I write by I1 plus I2 by 2, this gives me the percentage ripple, right?
Okay.
The percentage ripple of the flux. Since it is linearly, current is linearly related to the flux, so this gives me the percentage ripple of the
Percentage.
flux. So V in dTs by Lm times mm, P by V in D. So what I am getting from here is V in D goes away, so power time Ts by Lm, right?
Hmm.
Power time Ts by Lm. Is it matching? Dimension is matching? No, dimension is not, but something is wrong. Voltage into current is power. V is L di dt. Is V. V and D is gone. Power times T is energy. Energy by
That is
L.
1 of Li square divided by d ts.
Am I missing something?
The energy stored in the inductor primary is
No,
equal
no.
to 1
My
half
left
Li
hand
square.
side. My left hand side is dimension zero. Current by current.
Hmm.
It should also be dimension zero. Why is it not dimension zero? Average current is this. Current into voltage is power. P is this. V equals L D L M
The
D
ts is
by
equal to
dt.
energy divided by inductance. So
Oh, okay.
better
This
will
is this is this 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 is below this, na. This is in the denominator. I directly
uh,
multiplied it. This is V in D by P. V in D by P. Now you see, in this relation, we know almost every. Let us see what do we know. We know V in, that is given in the rating. We
okay.
know TS. We have decided at what frequency you want to operate. We have calculated D
Hmm.
already because we already decided what N1 and N2 we need, and from there we have calculated D.
Hmm.
Okay, so D we know, P we know, V in we know. So what is left is LM, right?
Hmm.
Now the thing is, this thing generally we keep say around 20%,
Hmm.
20%, 25%,
Hmm.
right? This is where we keep. So from here we can find out LM.
Hmm.
What is the magnetizing inductance that we need,
Hmm.
right? Now once we find out LM, you see, from 1 and 2 we have the values of I1 plus I2, we have the values of I1 minus I2 minus I1.
Hmm.
So solving this we can get the values of I2 and
And
I1.
hmm.
These two we can get. Now the next part is, this much Lm we need. Lm is
Primary
n
inductance
squared permeance,
permeance.
or n squared by reluctance. I remember after this calculation, we went into kind of iterative way of designing the magnetic field, a magnetic circuit. What we did is we went to the shop, because there are catalogs for
Code.
course, but not always the shopkeepers keep that. But they, I mean, they do not even have those catalogs or something. They have the course in their showcase. You have to look from there and buy something like that. So that's why we had to go in some iterative way. But the thing is, something like this, two important things are here. Let us consider the magnetic circuit, the core here, to be infinitely permeable. So the only reluctance that is being offered by is the air gap.
Air gap.
So if you have, what we do is we make the winding on the, sorry, we make the winding here. So this thing now becomes what? This thing now becomes a magnetic circuit whose equivalent electric circuit is like this. Okay, uh, all of them have certain width. Generally this width and this width are the same. So this is R1, this is R2, and sorry, this is R1, this is R1,
R1
and
plus R.
this is something R2. So my equivalent reluctance becomes R2 plus R1 by 2. So this is what we have,
Hmm.
right? So this reluctance, so we can put here, and putting the reluctance here, we can find out that if I use this core, how many number of turns I need, right?
Hmm.
So say I got this core, I got this number of turns. So I know how many number of turns n1 I need, and I also know how many number of turns n2 I need. Now the next step is whether I can do the winding. How to do that? My primary current looks like this. Primary current looks like this. My secondary current looks like this. So I have a primary current RMS. I can find out the RMS value of the primary current. Okay. Now the next step is the current density J. For this kind of transformer, since it is open in the air, we can take say J of around say 5.5 to 6. If 5.5, let us take 5.5 ampere per
Per
millimeter squared.
millimeter square.
Okay, so this is the J that we need, so let us call it J max. J max, right? So my I1 RMS times J max, sorry, now we have certain conductor area of conductor, required area of conductor, millimeter squared, and my I1 RMS, this should be equal to this J max, right? Sorry, this should be
Less
equal to
than
J max, less than, or if I talk
equal to.
about less than equal to J max, let us say we are designing at the boundary, so this should be equal to J max. So from here I can find out what is the area of conductor I need. Now the next step is to refer to the SWG table. If you need this area of conductor, there is no guarantee that you will get exactly this from the shop. Okay, so you have to go to the SWG table and you have to take the next higher area of cross section. Higher the value of SVG means thinner the wire. Okay, now you have certain AC prime, let us say. This is what you have got from the SWG table. So this is your total copper area. Now this will have insulation, let us say 20% insulation area, 1.2 times number of turns, I am writing them N1. So this is the area that your primary winding requires, plus similarly you have to calculate for the secondary winding. So this is the total area that your primary and secondary winding requires. Now the next thing that comes into picture is slot fill factor. Okay, slot fill factor, there are several things. Okay, let me tell you what it is. Say this is the window in which I am making the winding, my round winding. So they are like this. Forget hand winding, machine winding also cannot give you very large slot fill factor. In our case we used to hand wind, so we kept around, first we kept around 40%. It was difficult to accommodate 40% slot fill factor. Say around
Sir,
35 we design. Yeah,
sir, the slot fill factor, you mean that window area factor?
yes.
Okay.
So how much area you can utilize, how much area of the window you can utilize. So let us say that is 35%. So this divided by 0.35. This factor should be less or equal to the window area. This factor should be less. So what is window area? Window area is this area. Window area is this area. So our iterative process was like this. Now you see what you can do is, there are two things, two contradicting things that comes here, like most other designs. One thing is you have to use the smallest possible core. You can use you can go and buy a large core and use it directly. You don't have to worry about wind area and all, but your footnote, sorry, not footnote, your footprint will increase, weight will increase. So we have to use the smallest core and make sure that this condition is satisfied. So this is where we need iteration, and you may not go through iteration. In the book that I mentioned sometimes back, Professor V. Ramnarayan's book SMPC, there is a table. I do not remember it exactly, but there is a table where you will get to find the factor, wind area factor and all, from which you can choose the core. You can calculate which factors of core you need, and you can choose the core. But the problem is, what I said is that most of the shops, at least where I went, they do not keep the cores as per catalog or numbers. They have simply cores, and we have to choose one from them by wild case. So some 2-3 cores we bought, of which one we used. So this is the basis of it. There is an there is I think some 2-3 week later, next week only, there is magnetic circuit design in this course. So we will get to see more what the procedure is.
It is in week 9 lectures are there, sir.
Yes, next week only. What we
It
are
is in
discussing today is week 8.
8 lecture, but already it is there.
Okay, so this is the process for magnetic circuit design. And
Okay, thank you, sir.
One thing I jumped a step. I think you already know it, but still, reluctance is L by mu A. Since in this case we have considered that only the air gap is contributing in the reluctance, and we are not taking any fringing into account, so it is L by mu naught A. So what is L? L is nothing but the air gap length.
It is dominated
This.
by gap length.
Yes, it is this, and area A is the cross section area of the core. Whatever cross section area you have, that is the area. So this way you calculate the reluctance values offered by these air gaps, and say you find out that you need some 0.1, 0.2 mm maybe air gap length. What we used to do is we used to cut papers and fold it and measure the thickness with vernier calipers, and then put the papers here. That would create the air gap.
Yes, sir.
It's 7:27 already. You have any more question, or I will try to solve some textbook problems, means problems of last.
Sir,
Yeah.
so if, as you said already, if the current through the inductor is interrupted suddenly, which means that there is a current flowing through the inductor, and you are making the switch to the another position, and then thus making the current through the inductor, and there is a change in the inductor current. In that case, you said that there will be a fall in the inductor current. Is last week we had discussed. Is there is a if there is a fall in the inductor current? Suppose in the
Or at
last
least it will
assignment,
try to fall.
it will try to fall now, sir, which means that it is dissipating its energy to some other element.
Yes, it's trying to
It
dump
is
its energy somewhere else.
it is trying to jump its energy. So in the case of buck converter, when you're trying to open the when you're trying to open the switch, it is dissipating the energy to a diode or to a capacitor, sir.
Just a
To
minute.
where it is dissipating,
My
where
OneNote
it is
crashed.
dissipating energy.
Just a second, my OneNote crashed.
Okay.
Okay, let me see how much we have lost. Not lost much. See, the thing is, it is like this. Since we were concerned about our discussion on how the diode is turned on after this switch is
Okay, sir.
opened, I drew only this loop. Let us draw the whole loop. Okay, so if this is V in, say this is V SW, say this is V L, say this is V D, is V O. Okay. In this loop, we wrote the KVL that VL increasing plus VD plus VO equals 0. Okay, but we can write another KVL also here, which is VL plus VS. I've written VS. VS increase, increase. Increase. Right. So since last week we had this discussion that this VD comes out to be minus VL minus V naught. As soon as this switch is opened, this VL suddenly uh, current was flowing like this, right? So this VL suddenly becomes a negative. VO cannot change, so VD will start increasing and it will become 0 and the diode will turn on. Now what happens is this equation is also must also be kept, must also be must also hold good throughout. So here also it's the same thing. VL
So, one
suddenly,
second. So it can dissipate its energy to across the diode.
actually it tries to dissipate the energy across everything open that it gets in front of it.
Oh, okay.
Anything that is open in front of it. Why can I say, how can I say, like, because for the other components the voltage across them is defined, it is stiff.
Yes. V
Only
naught.
this diode
Across the capacitor is
voltage,
V naught.
yes, only the diode voltage, switch voltage, they only can get affected. Here also you see,
Oh,
as soon as I turn off the switch, VL, as I said, suddenly
okay.
becomes negative. So it suddenly
Oh,
dropped. This is fixed, this is fixed. So BVS will suddenly increase a lot. So if in
oh,
this buck converter,
oh,
in buck
okay.
converter, how do we do? In buck converter, we draw the, oh, it's, in buck converter, we draw the switch voltage like this. When the switch is closed, the voltage is like this. When the switch is open, the voltage is like this. But if you actually make a converter and look at the voltage of the switch, it actually looks like this. When it is closed, it is say when it is closed, it is say 0. But as soon as the switch is opened, because of this phenomena, that a sudden negative value of VL increases VS, will give you a voltage spike. If not this wide, a voltage spike, and then it will reduce
Okay.
again like this. So during this time, there is some energy lost in the switch, and you need either a snubber or maybe a heat sink, or maybe both. Snubber does not reduce the loss; it simply shifts the loss from the switch to itself, so that the switch is not damaged.
Okay.
The switch voltage looks like this. Let me see if I get some waveform online. Everyone is showing the ideal. No one is showing. No, I do not get.
Sir, actually, this
Yeah.
the wave shape similar to this
Hmm.
uh, can be seen across the switch in the forward converter, right? Voltage across the switch.
Yes, everywhere. If there is an inductor, this thing will happen. For leakage inductance, for forward converter, it will come to leakage. The leakage will completely get dissipated across the. I don't know for what converter they have made it. Can you see this blue colored waveform? Something like this will happen. This ringing comes due to stray inductances in the switch leads and all.
But we will not we will not see this ringing, right, sir?
Ring you will
Only
get to see. You will get to see because see the switch from the front it looks like this. No, here is the metallic part. A hole to attach the heatsink. You have the leads. We discussed this, I think. And this is the PCB on which you are mounting it. PCB or variable, whatever, mounting it with shoulder. So all these things they create, and the tracks on the PCB they create stray inductances in terms of nanohenry, and all the
yeah, yes.
stray components inductance capacitance they create this ringing, these oscillations.
So, sir, if this
Hmm.
is the case with the inductor in this last assignment problem number 1, sir, uh,
This
we have
year's
an last week, sir. Yes, last week.
last week assignment. Let me check whether the last
Yes,
it
sir.
is gone. Week 7.
Yes, sir. First one.
Okay. First one.
So when the switch is on, the inductor current is rising. Okay. When the switch is off, the inductor is dissipating through this diode, sir.
Just a minute. When it is closed, then
Okay.
it is rising. When it is open, it is not dissipating. Is it ideal diode?
Yes, sir. It's an
All the
ideal diode.
components are
Then
ideal. So see, it cannot
yes.
dissipate.
So in that, okay, then it maintains the constant current.
Just a minute. Which one is correct? Waveform of load current IL. What is IL? What is IL? That one is IL. If the switch is closed for this
Yes,
and
sir.
this, then opened. Yes, it will increase linearly, then stay constant.
Stay constant. So
Hmm.
as we have discussed here, like it, there will be a disturbance in the inductor current when there is a opening of the switch. There is
Hmm.
a disturbance in the inductor current. So
Hmm.
that is not be noted here, sir.
No, they have mentioned here na, that considered all the circuit components are ideal.
Okay.
So circuit components are ideal means everything is happening instantly. There is no delay.
Oh, okay.
This
Okay.
this peak this peak comes because the diode takes some time to turn on. If it turns on exactly when the and also the switch takes some time to turn off.
Okay.
If things are instant, if the switch instantly
Okay.
turns off and the diode instantly turns on, you will not get to see this
Okay.
peak.
Okay. Okay. Oh. Oh, this rate. So this disturbance is not seen as a switching is an instant one.
Hmm.
You mean to say? Oh.
There is a very small instantaneous disturbance in the inductor's current. It doesn't get a positive flow and it tries to
Okay.
dissipate the energy
Oh.
in the
Okay.
switch.
Oh, there will be a dip in the current, but since it's an ideal, it is not shown. That is the thing,
No,
sir.
dip in the current you will not get to see. Current cannot change fast in inductor. Current you will look
Okay.
continuous to you.
Oh, yes. Yes.
But the DIDT voltage is very large. A small change in a very short time also gives rise to a large voltage.
Oh. So here,
Yeah, go ahead, go ahead.
here then the inductor voltage would be the L di by dt. Then would be
Why? Which question? The question. This one you are
for
saying?
that only the same
Last.
thing. Yes, sir. Yes, sir. For the same thing.
This question.
Yes, sir. For the same thing.
So when the supply voltage is, I mean, when the switch is closed, then the inductor voltage is
Okay.
Vs 100 volt.
Yes, yes. When it is off.
That is zero.
Okay.
Because the diode is ideal,
The
so diode voltage is indicator voltage
yes,
0 volt.
a drop across at 0. Okay, sir.
Sir,
Yeah.
sir, in the transformers,
Hmm.
while we are drawing the equivalent circuit of the transformer, we draw the resistance and inductance in series with
Hmm.
the. So there we say that inductance we are drawing in series is because of the leakage inductance leakages in the transformer
Hmm.
core.
Hmm.
So how the leakage flux, that is the fringing flux, right? How that
Not
fringing flux is
fringing.
okay.
Leakage means flux produced by one coil
Does
which
not
is
link with
not
other.
linked by the other. Say if you have
Yeah, sir,
one
that's
winding
understood.
like this, we have one other like this, and if there is a flux line like this,
Mm,
then this is leakage flux.
yes, it is not
First
going
one,
to the
it
other
is leakage
winding. It
flux.
is linking with the same thing.
Hmm.
Uh, sir, this is the self inductance, right? Can this
No,
also be
this is
called a
leakage
self?
inductance. You can call this thing a self inductance.
That is mutual. This
Hmm.
is magnetizing. What is this, sir?
Oh, sorry. Is magnetizing the self inductance, isn't it?
Okay.
Because suppose I open circuit the secondary one, or maybe throw away the secondary one. Only this is here. Now I supply it with a voltage V. I will get a current V equals L di dt.
Yes.
This L is nothing but this L,
LM.
Lm,
Okay.
because I have thrown away the secondary. So this will anyway not conduct,
No
because
current.
that summation over Ni must hold good always. This must hold good. So this will not conduct if there is not secondary, if the secondary is open. So this L is this L, or in other we can say this L is Lm plus L leakage.
LM is L leakage means that is looking from the input side. The
Yes,
total
if I
inductance
am
is.
have voltage V here, then now there is IR also.
Sir, this leak, as you said, this leakage flux is nothing but this inductance in the series. Sir,
Hmm.
how from the leakage flux they are quantifying this inductance value? Oh, from quantifying this inductance in series, that is the leakage inductance.
There are tests now, open circuit, short circuit tests.
Okay. Mhm. Mhm.
From there we can find out everything.
Sir, can you say again how in ideal transformer this magnetizing inductance is very close to infinity?
It's not about how, it's how we define the ideal transformer.
Mhm.
Ideal transformer means when it is connected to the say this is an ideal transformer. That means this equation summation over Ni is 0. This will hold good. That means when the secondary is open, it will not draw any current from the supply. Only when you have a load here, it will draw a current I1 such that I1 and I2 are related as I1 A1 equals I2.
Okay. Sir, this MMF summation you have written Ni equal to 0. This relation will be valid at every instant. It
Yes,
has to.
yes. This is nothing but Ampere's circuital law.
Integral h dot dm.
Yes, we should go to problems now. 15 more minutes left. Okay, so this is the first problem that we have today. A flyback converter is supplied from a battery of 25 volt. The voltage across the load is 25 volt. Okay, so 25, 25, and drawing a current of 1 ampere. Load current is 1 ampere. The flyback converter switching is say operating at 25 kilowatts due to ratio of 0.6. The voltage withstanding ability of the switch should be at least this much of volts. Okay, so we will find out what is the voltage across the switch. So whenever you are solving any DC-DC converter problems, make sure that you are solving by drawing the waveforms and not trying to memorize the expressions. Okay, so this is the switching waveform. Say we have been asked to find out the voltage across the switch VSW. Now when the switch is on, the voltage across it is 0 because it is conducting, and when it is off, it has some positive voltage. So this is the voltage that we need to find out. Okay, now let us see how the circuit looks like when the switch is open. So when the switch is open, I have a voltage V1 here. This is my Vs. Let me write Vs. I have to write W again and again. Vs, and there is no current flowing through this, right? So this I1 is 0, but there is a current flowing here. This I1 is greater than 0. Some current is flowing. And since this diode is now forward biased, we have 25 volt here. We have 25 volt here. Let us not do it this way. Let us define V2 as this. Okay, see, I have put plus signs on the dot terminals for both V1 and V2. Since I have put plus sign on dot sides, I can write V1 by V2 equals N1 by N2. Okay, this is with sign, both are plus. And here what do we have? We have V2 equals minus 25 volt, right? Now we will write the KVL in the primary loop. So KVL would be V in equals V1 plus Vs. V1 plus Vs. Now what is V1? V1 is V2 times N1 by N2 plus Vs. We will put values now. So V in is 25, V2 is minus 25 times N1 by N2 plus Vs. So what do we have? Vs equals 1 plus N1 by N2 times 25. Now N value we have to find out. Okay, 1 is to n they have given. I have taken n1 by n2. How will you find n value from the voltage relation? We have output voltage for flyback converter. Output voltage is input voltage times n2 by n1 d by 1 minus d. In our case, v output by v input is 1, so we have 1 equals, let me put it the other, let me write it this side then. So we have n1, both are 25, right? So it is 1. n1 by n2 comes out to be d by 1 minus d. D is 0.6, so it is 6 by 4. n1 by n2 is 6 by 4. 3 by 2. So what we have is 3 by 2 plus 1, 5 by 2 times 25. So it should be 62.5. 2.5, 25 is 625 by 10, 2.5 volt. So this voltage that will appear across the switch is 62.5 volt. We have to have a switch which has a voltage withstanding capability of at least 62.5 volt. Just applying KVL. Make sure that you do not make mistake while writing this assumed positive direction of voltages. Always put the plus on the dotted or on the undotted, whatever. If you do that, then you can directly write this v1 by v2 equals n1 by n2. Then whatever value of v2 or v1 you get, write it from KVL and then put it in the equations. Then you will not need to worry about the signs.
Sir?
Yeah.
Sir, in this, while calculating this V2 as minus 25, is that because of the dots are in opposite terminal? We are writing this
No,
minus
no, no.
25?
See, it's step by step. You go. We first write the assumed positive direction in the transformers. How do we write? We do one thing, that we put plus on the dotted terminals. Even if you have 10 windings on the transformer, for all the winding you write plus on the dot side. Okay. If you do that, then while writing this equation, v1 by v2 equals n1 by n2, or maybe v1 by n1 equals v2 by n2 equals v3 by n3, you need not write minus anywhere. All will be plus. That is clear.
Yes, sir.
Now
Yes,
the
sir.
next part is just applying KVL in the secondary. You apply KVL in the secondary, you will get v2 equals minus 25 in the secondary loop. We are talking about switch voltage, so we are talking about off time. Off time means diode is on. So
the secondary side diode is on.
Yeah. So v2 plus 25 is 0. So v2 is minus 25. Alright, next question. Forward converter employs a flux reset circuitry that is lossy. Converter supplies a load of 20 watt at 50% duty ratio with the power semiconductor switch operating at 40 kilohertz. Input supply is this and negative band is this, and this. Considering ideal operation of semiconductor switches, calculate the percentage efficiency of converter. So we have what? We have the output power. Everything else is ideal except this thing. We have to find the efficiency. So if we can find out the loss in the resistance, that is enough to find out the efficiency, right? Now things are designed in such a fashion. If I draw the magnetizing current, looks like this. There may be some dead zone, there may not be some dead zone, depends on what value of resistance you have chosen. If you have chosen a large value of resistance, then there may not be a dead zone. No, sorry. Time period is L by R. Large R means small time. So large R means there will be a dead zone. It will dissipate first. Yes. But that hardly matters. What matters is our stored energy in the magnetizing inductance is dissipated completely in every cycle, right? So the energy that is stored in the magnetic circuit, or mean the Lm, energy stored in Lm, that is being lost in every cycle. So if I can find out the energy stored in Lm in every cycle, that is the loss, that times frequency. Okay, we'll see. So when the switch is closed, that is when energy is stored in the magnetizing inductance. So what do we have? We have V in equals Lm delta Im by, this delta Im is nothing but the Im peak, right? This is Im peak 0 to this value times dTs. So what do we have? This peak value of Im is equal to V in dTs by
L.
Lm. Now the energy that is being lost in every cycle is nothing but half Lm Im squared. So half Lm V in squared d squared. I am writing this as frequency squared, half Li squared. So it is half V in squared d squared frequency squared Lm, right? So this much energy is lost in every cycle. So what is the power loss? So this much is lost in every cycle. So how much is lost in a second? That is the power loss in watt. So that is nothing but frequency times energy loss. So that comes out to be half V in squared d squared by F Lm.
Ln square. Oh, sorry, sir.
Lm. So this is it. I think we have all data. So what do we have? We have half V in is 300. So 300 squared d is 0.5, 0.5 squared, frequency is 40 kilohertz into Lm, what is it, 10 million.
10 million.
So this becomes 400, 800, 300 squared times 0.5 squared by 800. Someone do it. And let me know the loss in watts. Quick.
So it is 28 watts.
28 watts, say approximately. So 28 watt is the loss. We know the output power 200 watt. So our efficiency is output by output plus loss. How much?
%.
How much?
The input power is 228, right?
Output is 200.
Yeah.
It's 87.71%.
Yes.
87.71% is a very, very low frequency for a power-electronic converter.
Efficient.
We want, like, we expect more than 96% at least.
Sir,
Yeah.
here this is lossy dissipation, no?
Yes.
Because of R and diode. If you
Yes.
put only diode, then it will be going to the regenerative mode.
No, it will not. It will. This current will keep flowing like this.
Okay, but that will if resistance is not there.
But that will defeat the whole
Uh,
purpose. No, then
no, we have reset winding and non-lossy reset winding.
that we discussed. Instead of resistance, we have the winding.
Only reset winding is there, and through diode it will go there.
Hmm.
Then it will be non-dissipative. Here we have put a lossy resetting.
Lossy DC. Just a minute. I think I drew one circuit wrong. Here I drew it wrong. I drew it correct for the first time. When I am turning this switch off, I want this to flow. No,
Uh,
did I draw it wrong? No, I didn't draw it wrong. I drew it correctly only. Just a minute. Where did it go? No, this was correct. Sorry, that
there
was
we
correct. This
have
is
to
different.
modify it.
No, forget that. That was correct.
Mm.
Yeah, what was your question?
If instead of this lossy reset, we have non-lossy reset.
That we discussed. Then we have to have inductor here.
Yes, 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 yes. Then it will be non-lossy reset.
Yes, Jagadish is asking why that R is needed. If we do not have R, then how will the inductor current look? Inductor current,
Inductor
it will
current will have
increase.
path through. It will
No,
increase and then it will
then
reset
stay
with the.
constant. No. Someone asked why is that R is needed. If you
Ah,
don't have R, then inductor current will look like this.
yes.
It will go into saturation, and at some point it will short circuit the supply voltage.
Yes.
Why short circuit? I think we discussed if L is there. No, see, we have to somehow move away that energy. L cannot dissipate energy. More we go into this zone, that means more we are going here. Inductance is n squared permeance. More we are here, lesser the permeance, so lesser the inductance. So V equals L di dt. So for a same voltage, if this drops due to saturation, current will see a sudden large increment
Large
and
increase.
short circuit the supply voltage.
Yes.
Means at this point this inductor is as good as a wire, just a wire, because the core is now as good as air.
Sir,
Yeah.
sir, in this lossless core,
Here, next problem it is there. It is
Yes,
that
yes.
non-lossy dissipation.
Yep, we'll do.
Here will it will happen that the efficiency
Yes,
will be more than what we have to dissipate to
yes.
reset.
The next one is ideally 100% efficient.
Yes, yes.
I mean theoretically 100% efficient.
There the question is different, no, sir?
We'll see. We'll see. We have a
We'll
question
see.
I think from you.
Okay, okay.
sir,
Yeah.
sir, in this lossless core reset,
Okay.
we are through the diode. We are with the territory. With the third winding through the diode, we are putting that back to the source. Sir, how how because this we are actually saying the energy stored in the inductor is fed back to the source. Sir, in that, how will be the current wave shape? Because if you dissipate through the resistor, it will be exponentially decrease.
Triangular. For resistance exponential, for everything is pure inductance here. So
Inductance, yes.
all the voltages, all the voltage equations here are nothing but V equals L di dt. Everything. So when this current is dissipating, this is going back. Then also basically what is happening, if you write the equation, we wrote this equation, sir, right here when we derived the relation. Where is it? Here, see this equation. It will be linear. So the source current will look like something like this.
Okay. Oh,
It is regenerative type.
sir.
Yes.
Sir, in that case, there will be momentary increase in the source voltage itself, right?
Actually, thing is, such cases we do with capacitors and all. Okay,
Okay.
so the current that is going back will actually be absorbed by the capacitor, and again when the switch is closed, energy will come back. So yes, the capacitor will experience a voltage ripple which will uh, be reflected as a increase or decrease of the source voltage.
Okay.
Here
So
also the
the source is not. If the source is not having the sinking ability, then we can use the
You
capacitor.
must have a capacitor. Suppose you are making this in a lab and you have an SMPS from which you are supplying, or maybe say you have a diode rectifier, simple diode rectifier from which you are supplying this forward converter. Then you must have a capacitor here. Otherwise, what will happen is to save your flyback converter, your rectifier will go. Why will the rectifier go? Again, the same
the
LDIDT voltage will be impressed across the diodes.
diodes.
Inductor will try to dump its energy in the diode, and the diode will not be able to handle that, and it will go away.
Here the capacitor will absorb that current ripple.
Capacitor can absorb, because for capacitor V equals, sorry, I equals C dV dt. I is C dV dt.
Hmm.
So there can be a large change of current,
Hmm.
and there will not be a large change in voltage.
Yes.
So capacitors, we can have current spikes. Inductor, we can have voltage spikes, not the other way around. Okay, I think we will be able to solve one more only. It's 8-6 already. Okay, we'll solve fast. Let us see. A forward converter employs a lossless flux reset for converter operation 72 volt. Voltage across load is 15 volt. Current is this. Forward converter primary switch is operating at this frequency, this duty ratio. Voltage is standing compared to the primary power similar switch we have placed. Again, the same thing. So we will look into the switch voltage when the switch is open. So if this is the switching function, then the switch voltage will look like this. Question is, how much is this, right? Again, we will draw the situation at situation when the switch is open. Now when the switch is open, many things are happening. This is a tertiary winding, this is the magnetizing inductance, this is the primary winding, this is the switch voltage that we are trying to find. Okay, this is my V1, this is my V3, this is Vn. Notice how I am always writing the plus in the dot side. Let us write KVL here. So we have Vin equals V1 plus Vs. Since we have put plus on the dot sides only, we can write V1 as N1 by N3 V3 plus Vs. All my small become capital, so smalls. Okay, V3. Now what is V3? Let us apply KVL here. V3 increase plus V in equals 0. So V3 is minus V in. So minus N1 by N3 V in plus V switch. So what do we have? We have V switch equals, this comes this side, 1 plus N1
By N3.
plus N3 times V in. They have given 1:1:1. So our N1 is equal to N3.
2 times
So it
V in.
becomes 2 V in. V in is 72 volts, so I need a 144 volt switch.
140 volt. It's true.
That is clear.
Yes.
Okay. If anyone else has doubt, you can ask.
Sir, we have to discuss that synchronous buck converter.
Synchronous buck.
Uh,
Okay,
how
I will
that
discuss
wave shape
next
is
week.
going to negative IL and primary side also it will draw some
Synchronous
negative.
buck. Synchronous buck. Is it different from opposite? No. Negative current. Why it is negative current? Okay, next we will discuss synchronous buck. What is
Oh,
it?
that second switch, no,
The
that will
diode
be
is
on
replaced by switch.
switch. The switch that can carry the negative current if it DCM mode.
Yes, DCM mode. Yes, yes, yes.
In DCM mode, it may carry negative
Okay,
current.
yes. Okay, we will discuss next day for sure. That is very interesting
Oh,
thing.
yes, yes.
We will discuss.
Okay. Thank you, sir.
Okay, we'll look at this question. What converter is this? This is forward.
Forward converter.
So forward converter with lossy reset circuit.
Loss
Value
it.
of resistance for freewheeling action of magnetizing inductance maintaining a time constant of this during off state. So time constant is nothing but
L
my
bar.
LM magnetizing inductance by
R.
whatever R we have here. And they are saying it is 0.25 times TS. What is the frequency? Frequency. Switching time, oh, they have directly given. So this times 50 10 to the minus 6.
Hmm.
Oh, what is the question? What I have to find? What is the value of the resistance? LM is given. LM is given. Oh, LM is given in the circuit. 100 millihenry. So we can find out R, right? Easy question. This is the answer. What is the value?
It's 8K.
8K is coming? Oh, I did it the opposite.
Yes, sir.
Sir, LM by R is equal to tau.
I wrote the opposite here. It will come 8K. I wrote this by this. Is the power loss by inductor the same as resistor? Inductor, there is no power loss. I think you are making a mistake here. See, what is happening is, if I draw the equivalent circuit of this transformer, then it is like this. This is the ideal transformer, and this is the magnetizing inductance. Okay. When you are turning on this switch, current is flowing in this ideal transformer, which is nothing but the reflected load current. Current is flowing in this magnetizing inductance. Now the current that is flowing in this magnetizing inductance, that is linearly increasing, and it is storing a half Li squared energy in the inductance. So we must find out a way to dissipate away or to move away this energy from the inductance, because energy is inductance is current. If we do not move away this current, it will become saturated every time, every cycle. It will become more and more and more saturated. So that is why we are dissipating the stored energy in inductance in the resistance. It's not the loss in inductance. Stored energy in inductance, every cycle, as much energy is getting stored, we are dissipating it in the resistance in this case, or giving it back to the source in this case.
Sir,
Yeah.
this half Li square, we have to dissipate in the resistor in the form of I RMS square R into 1 minus dTs. Right?
Yes. But you need not think it in that complicated way. Think it the way this problem says. Just make sure that your 1 minus dTs, that is the off time, is say around 3 to 4 times your time constant. maybe 5 times the time constant. If you do that,
So full dissipation
full
of that
dissipation can be ensured.
can ensure.
Okay, next question. Oh, last question is easier, discussed already 10 times. This is the last question, we'll complete it. Below figure shows a schematic circuit multiwinding flyback DC converter. What are the values of output voltages given DT ratio 0.6? Okay, so output voltage we know, right? Doesn't matter how many are here. Output voltage we just can calculate by N2 by N1 D by 1 minus D. N2 by N1 what divided 2 times D 0.6 by 4, so 3 times,
3 times.
because 72 volt. Second part is a bit tricky, not tricky, just maybe sometimes you go. What is the peak voltage stress across the switch? So flyback switch, did we discuss some time back?
The reflected voltage plus V in is
Yes.
the reflected voltage is very
Okay, we
is
did not. We'll quickly
well,
find out the same way.
uh,
This voltage plus the, so
reflected
let us
voltage.
let us let us consider a circuit of flyback with one secondary only.
Only
Then
we have to consider only one secondary here. If
yeah,
multi
that's
secondaries
that's
are
what
there,
we will discuss. So if there is only one secondary, let us forget the other one.
hmm,
Then what is the equation? The equation is V in equals V1 plus Vs, and it is minus n1 by n2 V out plus Vs. So Vs becomes n1 by n2. So the reflected secondary voltage plus the source voltage V
okay.
in.
So
Let
one of VO is plus V in.
V in, but that is for when one secondary is there. But now we have
Oh,
two secondaries. Thing is,
okay.
one more thing will come, that is n1 by n3 VO. Say, let us say it is VO2, it is VO3. Do you remember this discussion we just had?
So we have to add that much if the secondaries are more and more.
Yes, the stresses will become more and more.
More, more. So, okay. So it will be what? What
No,
is
just I was thinking, say these discussions that what we are having, this dot convention of transformers.
Yes, sir. Logically, also it is correct because if we have a continuous winding of, if we sum the voltages secondary, will be getting reflected at the primary.
So
Logically,
this
this has to be
what
added.
is this called? This dependent voltage source, more and more they keep coming
Hmm.
in
Yes,
series.
yes, 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 yes. It is logically also correct. It is okay. It is as good as a signal secondary. The secondary number of turns to be added. Okay,
Yes.
it is same. Then we have to add this N1 by N3 into VO3.
Okay. So in this case, N1 by N2 is same for both the cases, and voltages are also same. So it is half V2, half V2. So half VO plus half VO plus V in. So VO plus
VN
V in, 72 plus 24,
72 24
96.
96. Yes.
This somehow looks counterintuitive, right? I was also getting wrong.
Yes.
last question was this thing we have discussed 1,000 times. In the converter shown below, what happens if the duty ratio exceeds 50%? So it is 1 is to 1 is to 1, right? So we had that thing, n3 by n1 or n1 by n3. N3 by n1. So n3 by n1 equals 1 by d minus 1. In this case it is 1 equals 1 by d minus 1. So 1 plus 1 2, so d max is half. So what happens if the duty ratio goes beyond 50%? That is what we discussed, staircase saturation.
Inductor current is going to increase and increase and increase,
Increase and
like that,
increase. Ideally speaking,
till to
they will keep on
saturation.
increase like this. That would look like
Hmm.
a staircase, but it will not actually look like this. It will, the core will at one time become as good as air.
Hmm.
Means basically the source will be short circuited.
Hmm.
Okay, that's all for today. We're already 20 minutes more than time. Next day we will start discussion with synchronous buck converter,
Yes, yes,
why
sir.
it is used, where it is used, and the phenomena during uh, discontinuous conduction mode.
DCM mode, DCM mode.
Yes,
CCM mode I haven't any thought.
CCM is same as buck converter.
Same as
Yes,
buck, but DCM it is
yes,
tricky to
interesting.
understand.
Yes, we will discuss.
Okay,
That's all
thanks.
for today. Thank you. Bye.
Okay, thank you.
Thank you, sir. Good night.
Good night.